All right, good morning, everyone. So last lecture, we stopped at analyzing the largest eigenvalue of a matrix through an iterative method, right? So the procedure we have been following is this. So basically, we have a matrix A, and we want to compute the largest eigenvalue. So let's imagine we order the eigenvalues in terms of lambda 1, lambda 2, etc. to lambda n, where the magnitude of lambda I is always greater than the magnitude of the lambda I plus 1. All right, so we just order them from the largest to smallest. Okay, and we want to compute lambda 1. And by the end of the lecture, we'll generalize this procedure to computing not just lambda 1, but a series. Actually, we'll generalize just to compute lambda 1 and lambda 2. And as a homework, you are supposed to further generalize the procedure to compute lambda 1, lambda 2, and lambda 3. All right? And if you can do that, it's not that hard to generalize to compute like the largest n eigenvalues. So the procedure we have been following is to just construct a random x0. X0 is just completely random. And we compute a times x0 and a squared times x0, etc. to a to the kth power times x0, and k goes to infinity. And we just look at the magnitude of this vector to see how fast this magnitude grows exponentially. And the speed of that exponential growth is going to tell me the magnitude of the largest eigenvalue. So let's do some numerical analysis about this procedure and figure out how large do I need to make k in order to compute the eigenvalue to sufficient accuracy, no matter what the required accuracy is. Okay, so this goes like the following. So let's actually decompose A into the eigenvectors times a set of lambdas. Because we're assuming all the eigenvalues are distinct, this lambda would be exactly an diagonal matrix, right? So this lambda would be diagonal matrix formed with lambda 1 all the way to lambda n. So let's also express x0 as a linear combination of the first eigenvector corresponds to lambda 1 times a1 plus the second eigenvector plus etc. all the way to vn times an. And this can be written in matrix form, right? A linear combination can always be written in matrix form. That's just the v times the vector of a1 all the way to an, where v, each column of v is one of the eigenvectors. Okay? So now a times x0 would become v, we are substituting this formula, this representation of a, v times lambda times v inverse. We are also going to substitute the matrix form representation of our x0. That'll be a v times the vector a. So we'll denote this as just a vector of a. And of course, the v inverse times v cancels out, and we get v times lambda times a. Now let's focus on lambda times a. So lambda is a diagonal matrix, and a is a column vector, right? So lambda times a can be just written like lambda 1 a1, lambda 2 a. Oh, actually, it's a column vector, right? So lambda 2 times a2, etc. all the way to lambda n times an. And that multiplied with v can be written just as a linear combination of the different columns of v. So lambda 1 a1 times v1 plus lambda 2 a2 times v2 plus etc. Now what's interesting is that if you, instead of having a times x0, if you take a to the kth power times x0, everything is the same except for the eigenvalues would have a power of k. Here we'll just put k onto this, and these lambda k times a would be just having a kth power on all of these eigenvalues, right? Of course, because we know lambda 1 is greater than lambda 2 in magnitude, so the magnitude of the first term is going to be much larger than the magnitude of the second term, third term, etc., when k is raised to a high enough power. So here we'll just write this as just the leading term plus, I just use a big O notation, lambda 2 to the kth power, right? Okay, because everything other than the first term is either on the order of lambda 2 to the kth power or smaller, right? So the big O notation just is exactly designed to represent that. Okay. That means when we are looking at the magnitude of a to the kth power times x0, right? So if we look at the L2 norm of that, and we take the L2 norm to the power of 1 over k. Okay, so that is actually our estimate or our approximation of how big the lambda 1 is. So that is just going to be equal to the, well, the magnitude of this guy, right? Lambda 1 times a k, lambda 1 to the kth power a1 v1 plus o lambda 2 to the k to the 1 over kth power. Okay, so let's look at the influence of two sources of errors. The first source is the big O notation, right? That's proportional to lambda 2 to the kth power. The second source of error is from the initial contribution of the first eigenvector to the random initial vector x0. So these are the two independent sources of error, right? In the ideal condition, the second term is exactly 0, right? Basically, if we happen to choose an x0 that's exactly aligned with the first eigenvector, then the big O notation would have exactly 0 value. Also, if we happen to choose initial x0 whose contribution from the first eigenvector is exactly 1, right? The a1 is equal to 1. Then, because we are assuming all the eigenvectors are unit norm, so their norm is exactly equal to 1, then we would have no error. So this whole thing would be exactly the magnitude of lambda 1, right? So these two are, of course, ideal situations, and the fact that I'm randomizing x0 probably means there are contributions from the other terms, and a1 is not going to be exactly equal to 1. So let's look at these two independently. First of all, this. We can write this as the summation of two terms. One term, actually the product of two terms. One is this, to the 1 over kth power. And the second is a product, actually 1 plus a bigger, again, I'm going to use a big O notation of the ratio of the second term to the first term, right? So that's going to be the ratio, actually, let me just write it as something that's proportional to lambda 2 to the kth power divided by, actually, I'm also going to write a big O notation, something that's proportional to lambda 1 to the kth power raised to the power of 1 over k. And as we can see that the amount of error introduced by this, of course, as k goes to infinity, the power goes smaller and smaller, and this term also goes smaller and smaller. So basically, you can approximate it as the first term times 1 plus 1 over k times order of lambda 2 over lambda 1 to the kth power, right? So this is just a Taylor series expansion of a exponential function, where the 1 over k is this small number, right? Everybody agree with that?
If it's already, yes. So I didn't know how you drive that.
Yeah. So think of this as an exponential function, right? That this is the base and this is the exponent. So in this case, the exponent is very close to 0, right? What does an exponential function look like around the origin? Yeah, so if you look at an exponential function, we are going to be using Taylor series a lot in this lecture. So if you look at the exponential function, no matter what the base is, I mean, the base determines the slope of here. If it's the base of natural log, the slope is exactly equal to 1, right? Other bases have different slopes. But as long as the x-axis is close to 0, we basically have a linear function, right? So this is the linear function. I mean, the y-axis, the intercept is always 1, so that's where the 1 is, and the slope is really given by this. All right. Okay. So basically, the error caused by what we call the gap between adjacent eigenvalues really goes down exponentially. Right, so as you increase k, the difference between this term and 1 goes exponentially smaller and smaller. So so this term often dominates how much error you have for small k, right? Because in a lot of situations, the gap between adjacent eigenvalues, especially if you go to large systems, is actually pretty small, right? Maybe one eigenvalue has a magnitude of let's say 2, the second one has an eigenvalue magnitude of 1.99, right? So that means the gap is small and you have to raise it to high power to make it small. Yeah, you have a question?
So classical math, basically classical functions, when they have eigenfunctions, the gap becomes constant between eigenvalues and pi.
Yeah.
But this means that the gap goes 0, right?
What I'm implying is that for some dynamical systems, especially if you go to the chaotic regime, the gap between two different eigenvalues may be very, very small, right? So that's not the case for example, orthogonal polynomials, right? Yeah, so this thing can dominate the error when k is very small, but what's nice here is that when k becomes larger and larger, this term goes down exponentially, right? So we are pretty confident as long as we can make enough k, this goes to 0. Now the other source of error is from this, right? Is from the fact that a. Okay, so let me actually write this down a little bit more. So here, both the lambda 1 to the kth power and a are scalars, so we can put it out. And the v1 has a magnitude of 1, exactly. So this actually becomes the magnitude of lambda 1 to the kth power times a to the 1 over kth power, right? And that is exactly lambda 1 magnitude times a1 to the power of 1 over k. Right? Okay, again, this is an exponential function, right? With a base of a1. Maybe a1 is less than 0, which case the exponential function looks like that. But no matter what it is, as k goes higher and higher, this approaches a linear function, right? And the difference between this a1 to the power of 1 over k and 1, which gives our exact desired result, is proportional to what? Right? What is the difference between a1 to the 1 over kth power minus 1, right? The magnitude of this goes as k goes to infinity. How does it approach 0? I should write as tilde ups. Anybody? Yes, it goes down like 1 over k, right? Times the slope over here, right? Which I think is the natural log of a1, right? Okay, so we know that the error from the initial contribution of the first eigenvalue of the first eigenvector to the randomized initial seed goes down like 1 over k. So this is the error, because it's not converging exponentially. This would be the error that ultimately dominates how much error we have, right? As the error from the exponential contribution goes small enough. So these are the two terms that goes into the error of how much we have in the error of the computed eigenvalue. Okay, any questions on this? Okay, so now let's actually go to Python and look at what we did last time. Right, so we randomized a matrix, and we first computed the truth. Right, for a 4x4 matrix, is no problem computing the eigenvalues. But the procedure we are designing is really for computing the eigenvalues for something much larger, which just the call linear algebra.I doesn't really work, right? I mean, the cost of computing this is actually proportional to the cube of the size of the matrix, right? So if you have even if you have a matrix of several 100,000 states, it becomes pretty infeasible to compute the eigenvalue already. It's still doable. It may take a few hours on the biggest computer. I mean, like if you have a computer with lots of memory, right? It takes a few hours to get to the eigenvalues with let's say 100,000 by 100,000 matrix. But anything larger than that, it's pretty hopeless. Okay. So here we did a bunch of power iterations, and we have the magnitude, and we did a semi-log of the magnitude. But what's really interesting should be, let's make another, let's make actually, let's make two plots, and so let's actually plot the magnitude to the power. Okay, so I need to make magnitude and NumPy array. Then I can take it to the power of 1 divided by the 1 divided by k, right? Actually, it's +1, because I think let me actually just say the range of magnitude dot size. All right. Okay. I think I might not have imported the stuff I need to import. Unexpected EOF. Okay. All right. Magnitudes. All right. All right. So this is the exponential growth, and the second line tells me our estimate to the magnitude of this eigenvalue, right? So as you can see, the exact number is 2.55, and our estimate actually gets you to that number, maybe on the order of 40 iterations, right? Okay, and basically that's how you compute the largest eigenvalue. How about the eigenvector associated with that eigenvalue? Well, let's actually also print that. So this is the eigenvectors, all right, and it's actually pretty trivial in the sense that if you print v at the end, you're going to see that, oh, actually it's a bunch of infinities because we did that too much. So let's actually only plot, let's actually only do it for 400 iterations. So then what you see is that this v, of course, is going to be a very large, right? So but if you divide it by the largest magnitude, magnitudes minus 1, so that is going to be the magnitude of v. What you get is this, right? 0.304, 0.628, etc. And if you look at the first column of the matrix, v, right? So that's exactly the same as what we get. Okay, I mean, we can do a similar error analysis to that, and you're going to find out that the error in this v is actually going to be exactly the second component. I mean, there isn't even a first component in the eigenvector because because the magnitude doesn't matter to the eigenvector, right? So if you scale the eigenvector up and down, it's still an eigenvector, right? What only matters to the precision of the eigenvector computed is really the gap between the first and the second eigenvalues. By the way, do you have access to this notebook? I think I might have shared it on Canvas. If no, let me know. I should post the link.
I haven't checked Canvas though.
Okay. I'm going to check after class. I want to make sure like you have access to this, and you should also have access to this, the IPython notebook I'm working in class, right? So I think probably it's going to help you a lot in your homework. Okay.
This notebook, are you posting at the end of class every day, or is this like live?
I actually don't know. Like if I
You use the same one, right?
yeah, I use the same one, but what I hope is when I update it, it's automatically updated. So because in some of the online stuff, if I change it, it generates a new URL, and if I click on the old thing, it's still I think the IPython notebook is updated, so it should have the automatically updated one if you use the same URL.
Okay, I can check.
All right. Okay. So this is just to a linear system, right? So what we are really interested in is nonlinear systems. And for nonlinear systems, first of all, we want to generalize this matrix to a differential equation, right? So, and the second, we want to generalize from a linear differential equation to a nonlinear differential equation. So let's first take the first step, which is almost trivial. Okay, so what if you have a differential equation du dt equal to au instead of just a matrix multiplication? Well, it turns out that the solution to this equation, right, u as a function of t, can be written as e to the power of a times u0. where what is e to the power of a, where a is a matrix. So here, e to the power of a, it's simply, right, so if I can represent a equal to v times lambda times v inverse, e to the power of a is simply the same v times e to the lambda times v inverse. Well, now what is e to the lambda? Well, again, we have a e to the power of a matrix. Well, but e to the power of a diagonal matrix is super easy, right? So if this lambda is equal to lambda 1 to the lambda n, then e to the power of lambda is simply equal to e to the lambda 1, etc. e to the lambda n. So this solution is practically the same as what we analyzed, I think, in the last lecture or maybe last week. That is, we can always decouple that differential equation, right? We can decompose A into V lambda V inverse, and the different components of the differential equation, the different components of U0 that's aligned with different eigenvectors can be separated, right, into n independent differential equations that governs the evolution of the magnitudes of the contribution in each eigenvector direction. And because they are separated into n scalar differential equations, each scalar differential equation is just dA dt equal to 1 of the lambdas times a. They have a solution that goes like exponential functions. Right? Okay. Yes?
Equation u equals e raised to power of a is a function of time, right?
Oh, it's a function of time. Yeah. Sorry. So this is So this is there is a time in this. So basically, if a is So what's the right notation for this? So basically, what I mean is, if a is raised to this, this raised e to the a raised by the power of t is the following, and this would be e to the lambda 1t, e to the lambda 2t, and e to the lambda nt. Right. So that's really what I mean. Okay. Right, so maybe there should be a parenthesis on top of this, so that it is not a times t, but the matrix to the power of t. All right. Yeah, so this is really just a notation of taking the eigen decomposition of the matrix.
So that means essentially that the exponent is proportional to t.
That just means the exponent is proportional to t. So sorry, what does that mean?
Like, what we have there is e to the power of a times t, no?
E to the power of a times t.
We're just rescaling the matrix.
Yeah, just rescaling the matrix. Right. Yeah, that's right. So so that's right. So it actually doesn't. You don't need a parenthesis, right? You can just multiply a to t and take the exponent. Yeah, thanks. Yeah, that's right. Okay. Right. So once you have this, what we want is So here, instead of ordering the lambdas in terms of magnitude, we just order lambdas by the magnitude of e to the lambda. Okay, so what is the magnitude of e to the lambda? So suppose you can split lambda into real and imaginary parts. E to the lambda has a larger magnitude if it has a larger real component. So we are essentially ordering lambdas in terms of the real parts of lambdas. So imagine the real component of lambda 1 is greater than real component of lambda 2, etc. Right? And here, of course, if A is a real matrix, then and we're assuming all of them are distinct, has a distinct real parts, then all of them has to be real. But we are going to see we can generalize this to matrices that has both real and complex eigenvalues a little bit later. Okay, so if we order them in this way, then what we can find out is that computing the eigenvalues of this matrix is actually exactly the same as computing the largest magnitude eigenvalues in the last case, right? Because evolving this differential equation over a time of t, let's say t is an integer, is exactly raising the power of this matrix, raising the power of e to the a matrix, right, to the power of t. So we are essentially following the same algorithm. So starting with x0, so x0 being random, okay, and solve du dt equal to xu with u0 equal to x0 for t time. Okay, and then we are going to look at the magnitude of u at time t and take that to 1 over tth power. That gives you the magnitude of e to the lambda 1, right? So what that means is the real part of lambda 1 can be computed by taking the logarithm of this, is equal to the logarithm of u to the t magnitude to 1 over tth power, which is equal to 1 over t times the log of the magnitude, right? Okay, so let's try that on our IPython notebook. So I'm going to copy the same randomization, but going to, instead of a differential, instead of just a matrix multiplication, I'm going to do a differential equation. So let's look at the eigenvalue first. So my x0 is a random initial condition, and I'm going to define a function ddt du dt. So my u and time is going to give me a solution return dot a and u. All right, so that's my dynamics. Okay, and say from scipy dot integrate import od_int, and I'm gonna say u is going to be equal to od_int of du dt, and my initial condition is x0, and let's say let's say a range of let's do it 400. And in this case, let's actually subtract 0.5 so that A has both positive and negative contributions. Okay, so here let's plot the magnitude of u. So let me actually print u.shape. So u has 404. So the first dimension is the time dimension. Second is the spatial dimension. So let's actually take the square of u and sum it up only in the second dimension. So sum 1 means the second dimension, and take a square root of that. So that should have a length of time, right? So 400. So that's the magnitude for each time. And now instead of printing them, let's do semi-log y. Okay. Oh, not dot shape. Okay, again we see initially you can see it's a little bit weird, but after the initial transient we see a straight line going up, right? So that is consistent with our analysis that the logarithm of the magnitude should be proportional to t, and that proportional constant gives me the real value of the most positive eigenvalue. So let's do that. So let's actually copy the code I have previously. Going to do a semi-log of. I'm going to plot it on the first axis. Actually, let's do it side by side. And for the second, I'm going to plot the logarithm of the magnitude divided by t, which is a range of the shape u dot shape 0, right? So that's how many time we have. Okay. So we see that as time goes on, the computed eigenvalue converges to something like 0.71-ish. And that's actually exactly the largest eigenvalue over here, right, for a random matrix. So that's basically how the algorithm works. And the error analysis is exactly as before, right, because it's the same algorithm, but it just computes the exponential, the exponent of the largest, most positive eigenvalue instead. Again, the error for small t is probably going to be dominated by the gap between the two most positive eigenvalues, this one and this one, right? But for large t, it's going to be dominated by like the contribution of the largest eigenvector corresponding to the initial condition, which is random. And again, we can print out also the eigenvector, and we are also going to be print u minus 1 divided by the square root of u minus 1 square dot sum. So that's the magnitude. So if we do that, yeah, so the most positive one in this case is the last one, right? Still, the last one is the most positive. And if we look at the eigenvector, it should correspond to the last column of the matrix, which is this one. There is a sign flip, right? Eigenvector that doesn't care about the sign. 29793043. So that's exactly the same as this. All right. Okay. Any questions regarding this? If no, let's actually go to a nonlinear system. Yes?
Well, I was wondering if the biggest number is now it's technically a negative number. So does this not really capture like negative eigenvalues, or do they all have to be negative?
This captures the most positive eigenvalues. It doesn't. It doesn't capture the most negative one, even if the magnitude is going to be large.
I was wondering if this procedure worked on negative numbers. Like if all the eigenvalues were negative, would it still work?
It'll still pick out the most positive one, which is the least negative one.
Okay.
Yeah. So for example, how do we make negative eigenvalues? Just to make it -1, right? Here you get a bunch of negative eigenvalues, and the least negative ones are actually this complex pair, if I look at it correctly. Okay, so minus 0.0744, that's the real part, right? So you can see this goes down, right? And right, so the magnitude of the eigenvalue we computed roughly converges to that number. We are not taking enough iterations in this case, but yeah, as you go on, it should be roughly equal to the real part of these eigenvalues.
When the eigenvalue is positive, it means that our system is unstable, right?
Yes.
So if there's the first eigenvalue is negative, the second one is positive, it takes the positive value. So I mean, we can use it to see if our system is unstable or stable.
Yes, exactly. So if the most positive eigenvalue is positive, right, the system is unstable. I mean, this is actually closely related to the stability analysis, right?
So we can use it to see if the most positive is negative. I mean, for example, here, means the system is completely stable.
Yes. This tells you the system is stable, and it also tells you how stable or how unstable it is, right? So if you get eigenvalue that's close to 0 and slightly negative, it means there is a very lightly damped mode here. Actually, that's actually exactly what's happening over here. Okay.
I guess another quick observation is the eigenvector is now off, but I guess that might just be convergence.
Okay. So the numerical analysis I did was for eigenvalues that are has distinct magnitudes. So here, there are two eigenvalues of the same real part. The analysis is a bit more complicated, but like you can only ensure that this V I computed is a linear combination of the two eigenvectors corresponding to these two eigenvalues of the same magnitude. So if you, I mean, this is probably too much to actually just to look at the numbers doesn't work, but like we can pretty be sure that actually this is going to be a linear combination of the second column and the third column. Yeah. Okay, you guys can see it. Yeah. Anyway, I'm not sure because the combination can be actually complex combinations, right? You can multiply one complex number to this one and add it to another complex number multiplied by this one. So it's very hard to see in this case. Okay. Anyway, so let's any other questions regarding this before we go to nonlinear systems? Okay, so let's go to nonlinear systems, and again we'll use the most simple case. That's the Lorentz equation. So we'll just copy the Lorentz over here and just duplicate it at the end of the notebook. Okay. Previously, we did compute the stability properties of the Lorentz system around the origin, right? This is the evolution of 1,000 trajectories around the origin, and we did compute the eigenvalues and the eigenvectors. The eigenvalues are like these, and we see the least negative or the most positive eigenvalue is minus 0.47, right? So this is the target of our current algorithm before we generalize to computing more eigenvalues and more eigenvectors. So let's take a look at how do we compute this one. And let's actually copy these so that we actually have a baseline to compare against. Okay, so these are the 3 eigenvalues. Now let's do something very similar to what we did previously. Let's just take a random x0 and integrate. Okay, and let's actually plot the same thing. So we are taking a random x0. In this case, the dimension of the system is 3, and we integrate again like over 400 time units. And let's see how the plot looks like in this case. Let's just get rid of this one. Oh, not DUDT, Lorentz, yeah. What else do I need to change? Not much, right? Okay. Okay, so we do see a rapid decline, and then we get to these kind of a random, almost like oscillations, and then so basically this is very different from what we saw before, right? So let's actually only do it for instead of a 400, let's see, do 40 or 30 time units and see, and then we'll see what makes the algorithm break down at later steps. Okay, so over 40 units, we do see a straight line going down. And if you look at the convergence of the estimated eigenvalue, it is actually pretty similar to minus 0.475, right? So that's exactly what the axis tells us. But as the magnitude of u goes down to about 10 to the minus 6 or 5, so let's actually make it go to 50, something becomes weird, right? And we no longer have the nice trend of convergence. Why do you think that becomes the case?
You specified the amount of error before, right?
We specified what?
Yeah, here, epsilon. It's related to the epsilon.
Oh, the epsilon is only used to compute this, right? So if you comment out this section, epsilon is actually not used. Epsilon is actually not used in this analysis. It's used to get the exact answer over here. What happens? Somehow I'm off the internet. Okay, it's connected back again. Yeah. So if I comment this out, we don't have the exact answer, but we also it doesn't affect the iterative scheme. Yeah. So what happens over here? Any guesses?
Also, this procedure was for linear system, so that's why, because it's a nonlinear, that may have some problem.
Well, that's a good guess, right? So your guess is the procedures for linear systems, we have a nonlinear system here, and somehow the nonlinearity breaks it down. Well, I'm going to show you something a little bit interesting. So I'm going to make u equal to numpy.array u float 32. Okay, and I'm going to run this again. So you see this breaks down around the time 40. It still breaks down at time 40. Sorry? Yeah, so if we do it 64, I don't know, it breaks down at the same time. Yeah. So what this is doing is essentially, okay. So maybe it is not related to the round of error over here, but the precision of ODE int. So essentially, when the numbers are small enough, right? Either a round of error triggered over here, or the tolerance of ODE int is going to kick into effect. And that's going to limit the precision of the time integration I'm looking at here. Okay, so that's going to ultimately affect things. So if you have time, you can look at the tolerances. So relative tolerance, A tolerance. Let me try things here. Auto, let's say e to the minus 12. So that might fix. Yeah, so that fixes the error here, but if I integrate it for even longer, it'll show up at some later time. So yeah, so you have proposed a good solution to this, right? So that's something we can do to periodically normalize the magnitude. So how does that work? So let me go back to here is how do we do this for nonlinear systems. So basically what we're seeing here is analogous to the round-off error. So that's the error that happens when the magnitude of the solution is too small, right? And we're going to see later on, we are also going to encounter a different type of error. That's the truncation error. But in both cases, the solution to round-off error or truncation error is to make the magnitude of the perturbation neither too small nor too large. Too small, we're going to incur round-off errors. Too large, we're going to incur truncation errors. Okay, so in this case, if we want to carry out the iteration to longer and longer time, what we do is we want to make a iteration around the ODE int loop. So for, let's say I goes to range. Now this time we can make it 500. Now each time, each time I'm going to be integrating over just one time unit. Okay, so from 0 to 1, that's the time. And I'm going to be setting my x0 back to u at the last solution, right? The last time step. So if I just do this, I would be doing exactly the same thing, right? So so let me say ui is equal to this, and my u is going to be equal to x0 to start, and I'm going to be u dot append u0 minus 1. Right, so basically let's see, u is equal to array u. So this would be exactly the same as what I did before, right? If I integrate ui, if I integrate that's ui. If I integrate for 50 time units, I get this. If I integrate for 500 time units, that still works. Let me just get rid of the auto and ato, right? So if I integrate for 500 time units, that still works. Okay, so what I guess is the tolerance actually depends on the initial condition. So if the initial condition is small, ODE int actually adjusts the tolerance to fit, to kind of adjust it to the initial condition. So if I pass the initial condition that's smaller, it keeps it being small. But the real trick I'm suggesting here is instead of setting x0 to just the last solution, we actually normalize the x0 so that it's always magnitude 1. Okay, so here let me just say u mag is equal to square root of ui, the last solution, squared and summed. So that's the L2 norm, right? The magnitude of the last solution. So x0 is divided by u mag. Okay, and then how does that? So let's actually look at this. We are going to see that this procedure doesn't work anymore, because as time goes on, the magnitude of u, right, is going to be kept pretty much at a constant level, because every time the solution in this case becomes smaller, right, because the system is stable. But before it can get smaller, I normalized it so that it is always actually magnitude equal to 1, right? Okay, so when I look at these successively smaller, so it is no longer, the magnitude is no longer getting smaller. That's why when I divide the magnitude by the length of the time integration, we no longer recover the leading eigenvalue. So what is the solution to this? The key insight into fixing this algorithm while rescaling is actually the linearity assumption. Okay, we are solving the equation with an x0, but if the system is linear, okay, and we are assuming linearity in the neighborhood of the fixed point, if the system is linear, then the solution would be proportional to the solution I get if I did not divide by the u magnitude, right? So what that means is that if I actually store the magnitude of the u's and then multiply them repeatedly, then I would actually be able to recover the solution. Okay, so let me illustrate what I actually mean. So what I can do is before the ODE int, right, I'm going to be normalizing the magnitude. So let's say okay, so let me just compute the magnitude of x0, and x0 is equal to x0 divided by x0 magnitude. I compute the solution, but at the end of the solution, I'm going to be multiplying back with the magnitude of the solution, right? So here I can say x0 divide by x0 mag, and at the end I'm going to multiply the whole solution by x0 mag. So that way we are essentially getting the solution all the way, right?
You multiply by u or ui?
Oh, ui, yeah, thank you. Okay, so this is basically our linearity assumption. So that oh, okay, so I should be appending this before I renormalized it, right? So the 1 second. No, did I update x0? Oh yeah, I didn't yeah, right, thanks. So x0 would be ui minus 1, right? Okay.
You need the minus 1. UI is just 1 by 3 vector, right?
Yeah, so ui should have ui should be a vector of 2 by 3, right? Because yeah, it's 2 by 3. Okay. Appending the UI minus 1. So UI actually became very small. Yeah. Okay, so what I'm suspecting is that I need to actually copy this. Right, so you don't, okay, not copy this, but when I appended it into U, I may need to make a copy so that yeah, so that U is you actually right. If I don't make a copy, what actually happens? Yeah, if I don't make a copy, what happens is x0. Yeah, x0 is basically not a copy of the last element of UI. It's just a reference of the last row of UI. And then when I do x0 divide equal to x0 mag, it basically rescales the last row of UI, which is actually what appeared, which is what appended in the previous U, right? So that's basically a big difference when you switch from MATLAB to Python. Is everything is by reference, and this can sometimes throw you off. Yeah. Right, so do you understand why making a copy makes a difference? Okay. Anyway, so this is basically almost exactly the same as the previous algorithm that computes you the eigenvalue of the most positive eigenvalue, right? So let me just print out again the most positive eigenvalue. Should be about minus 0.4-ish, but this is like minus 0.6-ish. Is there still a bug somewhere?
Do we need to use copy for the last row in the loop, the last line in the loop, or not?
Nope. Can anybody think of why this doesn't compute the right eigenvalue?
Right after the iteration of you.
Okay, so let me fix this. Let me fix this by doing the following. So what am I doing here? Instead of making the magnitude of x0 to be 1, I'm making the magnitude of x0 to be 10 to the minus 6. Now we are computing something close to this. Why did that work? Because we are now dealing with a nonlinear system, right? So a nonlinear system not just have a round of errors, but also have truncation errors. So essentially, when we are feeding the initial solution to the ODE int, we want to make sure that the solution we get is neither too close to the fixed point, which is going to incur round of errors when we do the subtraction, right? it is also shouldn't be too far away from the fixed point. Otherwise, we are going to have truncation errors. Okay, and 10 to the minus 6, at least the for Lorentz system, seems to be like the sweet spot of shouldn't be too far away, shouldn't be too close. You can deal with the truncation error a little bit better if you initiate a pair of solutions, one perturbed in one way, the other perturbed in the other way. And you can use central difference, right, as opposed to one-sided difference. To that helps you helps you with making sure that the truncation error goes like the square of the magnitude rather than just the magnitude itself, right? So I mean, if you studied the numerical analysis, that's the difference between like a second order finite difference and the first order finite difference. Okay, and round-off error, there is really no way to defeat that other than making sure the perturbation is large compared to the floating point precision. If you are using double precision, okay. So here I'm using ODE int, which has its own. So let me run it for a little bit longer, and you can see. You should be able to see the round-off error if I make it too small, right? So if I make it 10 to the 19, then we are still getting something pretty good. Actually, let me get back. So this is not a good example for showing round-off errors. So maybe next lecture we'll show the round-off errors when we are looking at a fixed point, not centered at 0. Yeah.
Just a quick question. So how did you estimate that rescaling factor? Like, how did you know it's e to the power of 6?
How do I know if it's e to the power of 6, right? So let me actually get back to that in the next lecture, which we are going to analyze the same Lorentz system, but not around the 0 fixed point, but at a fixed point at one of these centers, right? So then we'll actually see the round-off error very clearly, because now we are subtracting the solution here from a fixed point, right? So the round-off error really comes through the subtraction. So let me actually illustrate it over here. If you are just saying, okay, if I do 10 to the minus 200 minus 0, that's still going to give me a precise answer, right? But if I'm going to, that's basically if the fixed point is at 0. If the fixed point is at 1, if I do 1 plus e to the minus 200, then subtract it from 1, I'm not going to get the right answer. I'm going to get 0, right? And in fact, even 10 to the minus 20 wouldn't work, okay? So you have to really get to about 10 to the minus 17 also doesn't work. I think 14 has to work, right? It's you can see there is it's not accurate anymore, right? So 10 to the if a perturbation of 10 to the minus 15 already have about 11% error, round-off error in it. While if the fixed point is at 0, even 10 to the minus 200 would work. Even 10 to the minus 300 would work. You have to go all the way to, I think, 320 or something, 50, yeah. So somewhere between 10 to the minus 320 and 350, the floating point stops working. Right, so basically the round-off error is vastly different if you are looking at if you're perturbing from a 0 point versus perturbing from something finite. All right. Does it make sense? I mean, so if you're not familiar with how computers represent a floating point numbers, I can give you a very quick overview. Maybe the next lecture when we actually start to look at the perturbation around the non-zero fixed point, and we'll actually do a more rigorous analysis of truncation versus round-off errors. Okay. All right. So let's leave this to the next lecture when we do a little bit more stuff. And I want to cover how to compute more eigenvalues of large systems. So basically the question is, if I want to compute 2 eigenvalues as opposed to 1 eigenvalue, what do I do? So there is actually a lot of different methods, but what I want to talk about is one method that is known to generalize to unsteady and chaotic systems. Okay, so not, if you actually just want to compute, let's say, 2 of the largest eigenvalues, this is not the best, the most efficient method to use. But this is the method that generalizes actually to chaotic systems, which we will study later. Okay, so instead of having just a random x0, we have a random x0 and x1, both random and different. Okay, and we are going to compute ax0 and ax1. So again, we are going back to the scenario when we are looking at a map instead of a differential equation, and then we can see like how do we convert from a map to differential equation by taking the exponent of the matrix. Okay, now instead of just keep taking the power, instead of multiplying a with ax0 and a with ax1, I'm going to orthogonalize these 2 vectors. Okay, I'm going to say, so here is what I'm going to say. I'm going to say x0 is equal to x0 divided by the magnitude of x0. So what I'm doing is what's called a Gram-Schmidt orthonormalization. Okay, x1 is going to be equal to x1 minus a okay, so what I'm going to do is I'm going to say x1 is equal to let me just call r01 times, sorry, so this is ax0, this is ax0, and this is also the magnitude of ax0. Okay, here is ax1, and I'm going to take a superscript to say what iteration it is. So x1 to the iteration 1 is equal to this, and the initial condition is iteration 0. Okay. Okay, so basically x1 is a normalized version of ax0 at iteration 0, and x1 at iteration 1 is not just a normalized version but an orthogonalized version with respect to the first component, divided by again the magnitude of this thing. Is it one second? Yeah, is it clear what we are doing here? So basically we multiply the vectors with the matrix, right? Then we make this unit a unit vector, and then and this R01 is set such that x0 dot with x1 is equal to 0. Okay, so what we're doing is that we are computing x01 so that we are projecting the component from ax1 and then normalize it. R01 is basically whatever that needs to be so that the numerator is orthogonal to x0. Okay, so for example, let me just illustrate as a code over here. So x0, x1 is going to be random.rand 2 and 4, so that where a is going to be. Okay, so let me just illustrate the procedure here. So what I'm going to be doing is x0 new, okay, is going to be dot a and x0. And then x0 new is going to be divided by the square root of dot x0 new, x0 new. Right? So that's make it a unit vector. x1 new is going to be dot of a and x1. But before I normalize it, I want to orthogonalize it. So x1 new is minus equal to x0 new times the dot product of x1 new and x0 new. Okay, because x0 new is already a unit vector, right? This dot product is what is needed to make x1 new orthogonal to x0 new. Okay, so right, so basically, if you take the if you take the dot product of this the result of this subtraction with x0 new, you should get 0. And then finally, I'm going to be doing the same thing but with x1 new. So this is the procedure.
So this is just QR, right, of new basis.
Yes, alternatively, you can represent it as a QR factorization. So alternatively, if you denote x0 as a n by 2 matrix of x0, 0 and x1, 0, okay, and then multiply a with the x0, what you can say is that this is actually equal to the new vector, which is x1, right? So x1 again is a n by 2 matrix, x0, 1 and x1, 1. So this matrix times a matrix that is okay. So let me denote R00 as this magnitude, okay, as the magnitude of x, and I'm also going to denote R11 as the magnitude, basically the denominator. Then what we see is that first of all, a times x0, which is the first column of the left-hand side, is simply equal to R00 times x01, which is the first column of the right-hand side, right? So if I put R00 and 0 here, then the first column of left-hand side is going to be equal to the first column of the right-hand side. All right? Because, I mean, this first column is the two coefficients multiplied by the two columns of x1, right, for a linear combination. And that's exactly equal to the first column of the left-hand side. And the second column of the left-hand side is equal to ax1, right? And if you look at this equation, I'm going to annotate it. This equation is the same as the denominator is R11. So R11 times x11 is going to be equal to ax10 minus R01 x01, right? Or if you move it to the left-hand side, basically R01 times x01 plus R11 times x11 is equal to the ax10. That's the second column of the left-hand side. And therefore, the second column of the right-hand side has to be this, which if I fill it, is going to be R01 and R11. Make sense? I mean, this is just the algebra. It's similar to what?
Algorithm called randomized sketch marks algorithm used orthogonal projection for.
I'm not familiar with that. Maybe if you can send me a reference, I can take a look.
Okay.
Yeah.
Maybe I can find it.
Okay, yeah, thanks. Yeah, so the fact that x1, the two columns of x1 are orthonormal, right? They are orthogonal to each other and both column has a unit magnitude, means that X1 matrix is a orthonormal matrix, right? And also this matrix is a upper triangular matrix. So this is equivalent of computing A times X0 and then performing a QR factorization of the product, right? So basically, this is like the Q, this is like the R. So if you perform a QR factorization, it is equivalent. Actually, the Gram-Schmidt orthonormalization is one way of computing the QR factorization of a matrix. All right. So, okay. So what is the result of this? The result of this is that you can actually compute the determinant of okay, so let me just do it in a very quick way. Is that now you can take the iteration on and on, right? You can say, okay, you can take this iteration on, and as you perform many iterations, a to the kth power of x0 is going to be equal to xk, which again is an orthonormal matrix, multiplied with many of these R matrices. So for example, if I call this R1, and the second time do it, I make it R2. So this will be R1. Actually, let me see which way is it. Yeah, R1 times R2, R3, etc., all the way to RK. And the product of a bunch of upper triangular matrix is an upper triangular matrix. Let's denote it R from 1 to K. All right. Okay. So then what's interesting is that if you take the transpose of this and multiply it with itself, AKX0 transpose AKX0, and that's going to be equal to the orthonormality of the matrix is going to make it cancel out. What you get is R from 1 to K transpose R to the 1 to K. Okay, and you can analyze the determinant of this matrix, and it turns out that the determinant of this matrix as time goes on and on is just going to be equal to the first eigenvalue to the kth power times the second eigenvalue to the kth power squared, right? Because there is a multiplication with itself. And of course, the determinant of this is going to be the product of the diagonal entries of the upper triangular matrix squared. So essentially, through this procedure, you can converge to, of course, you also take this, you can go from the product of the diagonal entries of the upper triangular matrix to the product of the leading two eigenvalues. Okay, and then you go back to our original algorithm, which computes the first eigenvalue. That allows you to infer what is the second largest eigenvalue. All right. Okay, so this lecture is going to end over here, and the next lecture we'll start doing some error analysis. We'll show you why this is the case, and we'll also show you how much error it is in this iterative procedure, right? And from there, we'll also demonstrate how do we do this for some real systems like the Lorentz equation, both at the origin and at a different fixed point. All right, okay, so I'll see you, and I'll put some homework on the internet on Canvas by the end of today, and it'll be due next week. It'll be basically exercise of this system to this algorithm to some larger equations. All right, cool. I'll see you next week.